All right, it's 8:30. Let's go and get started. All right, good morning, everybody. Thanks again for being flexible today and meeting over Zoom. I'll try not to make a habit of this, but sometimes I have to stay home, and it's this class is early in the morning. So thank you guys for meeting over Zoom. How's the audio? Is the audio okay? I kind of hear an echo on my side. Do you guys hear that too? Okay, the audio is good. Okay. Okay, if the audio ever gets weird, just let me know. My home setup right now is not really ideal for for streaming, so just let me know if you guys ever have problems hearing or if there's a prominent echo. Okay. All right, so with that said, let's go ahead and get started today. So today is the last day of our Laplace section, and so we're going to be going over a special function called an impulse function. And we're going to see how that factors into our ordinary differential equations. All right, so just a couple of reminders. So a reminder that homework 3 is due on Sunday of this week, right? So originally it was due on Friday, but because we had the guest speaker last week, everything got pushed back a little bit. So I want to make sure that after today that you have enough time to finish the homework. So basically all we're going over today is just homework problem 5 on the homework. Which is probably the fastest problem I would say of the homework. So hopefully, you guys' homework is in a good position. Impulse functions really aren't that bad. It's kind of like the easy ending to kind of what otherwise is a very difficult section. Okay. All right, and remember that our midterm exam is next Thursday. So and remember the midterm exam is going to be in person, and so it is the opposite of today. And so please plan to be in class on Thursday because there's no plans for the midterm exam to be offered virtually. Remember, you can have a cheat sheet, you can have a calculator, you can have a writing utensil, so you can have all of those things. And make sure you're using the study guide. So was everyone able to find the study guide okay on the website? All right, question, do we have to write the table on our cheat sheet? No, you don't. So I'll provide the Laplace transform table, so you don't have to write that on your cheat sheet. Yeah, that's something I can provide really easily. The cheat sheet should just be your own notes in terms of how you interpret the data, how you interpret the content, how you kind of organize the content. But any kind of essential kind of things like that table, I'll provide for you. Yeah. Okay, so are there any questions on the midterm or any questions about the homework or anything I can answer before we get started for today? Okay, all right, so let's go ahead and get started. And so the subject for today is going to be impulse functions. Okay, so we've done question 3B on the homework. Okay, we can go over that really quickly. Let me bring that up. 3B. Okay. So let's do that one. Let's do that one really quickly first. Okay, so 3B on the homework, we have y double prime plus 64y is equal to cosh of t, and we have y of 0 is equal to 1, and y prime of 0 is equal to 0. Okay, so this is our differential equation, and so if you wanted to, remember, cosh of t is nothing more than just we can represent that using exponential functions, right? And so one thing that you can do is you can set this equal to 1/2 e to the t minus, or plus, excuse me, plus e to the minus t. Okay. So if you take the Laplace transform of cosh of t, you end up with kind of the same thing. But if it's easier to kind of treat it as two different terms, then that's something that you can do. Okay. Okay. So let's go ahead and take the Laplace transform of this entire equation. Okay. Right, and so we take the Laplace transform of the left-hand side. We have Laplace transform of y double prime. That's s squared y of s minus s y of 0 minus y prime of 0. Okay, plus 64 big y of s. And then we have the Laplace transform of cosh of t. Okay, so let me pull up the table. So cosh of t, the Laplace transform for that is going to be s over s squared minus a squared. But in this case, a is 1 because there's a 1 in front of the t here. So s squared minus 1. Okay. Okay, so let's go ahead and work on this. And so let's plug in for our initial conditions. So y prime of 0 is equal to 0. And so we can go ahead and plug that in. Y of 0 is equal to 1. And so we can go ahead and plug that one in right there. Okay. And so if we group the like terms, and so we group all the like terms with y of s, we end up with s squared plus 64 big Y of s minus s is equal to s. And over here, I'm going to split the denominator. And so the denominator is s squared minus 1. And so we know this is equal to s plus 1, s minus 1. Okay. Okay, so let's go ahead and move this minus s over to the other side of the equation. And so we have s squared plus 64 big Y of s is equal to s over s plus 1, s minus 1 plus s.
Hey, Professor.
Yes.
Isn't the right-hand side in the original 3 cosh t?
3 cosh t, you are correct. Yes. So there should be a 3 here. Thank you for catching up. Yes. Okay. Okay. And so from here, we can just isolate y of s. So let's divide by s squared plus 64. And so we have y of s is equal to 3s divided by s squared plus 64, s plus 1, s minus 1, plus s over s squared plus 64. Okay. Okay. So now we have to inverse this. And so the inverse of this, on the one hand, we have right here, this term right here. So this term is already in a good form. So we know this is going to inverse into something like cosine of t. In fact, it's going to be cosine of 8t. Okay. Because if we replace the 64 here by 8 squared, we know that that's going to be, that's basically this form of cosine t. And so we just have to kind of move that around a little bit. Okay. Of course, the big question here is going to be this term right here, right? And so, of course, to work on this one, we need to do partial fraction decomposition. And that's where probably the bulk of this work is for this problem. Okay, so let's go ahead and I'll start it for you guys, but of course, doing the whole thing, I want to make sure I have enough time to cover impulse functions today, but I'll go ahead and show you the form. Okay, so 3s divided by s squared plus 64, s plus 1, s minus 1. Okay, and so this is going to end up splitting into 4 different terms. And so we have our first term, which is over s squared plus 64. We can't factor that one because it's it's an unfactorable quadratic. Then we have a term over s plus 1. Then we have another term over s minus 1. Oops. Okay. And so let's look at the numerators for these. And so if we look at the s plus 1, s minus 1, those ones are just linear polynomials on the bottom. And so on the numerator, we know we're just going to have just a constant, right? So I'll call this c and d. Meanwhile, for the s squared plus 64 term, this is a quadratic omni-denominator. And so our numerator here has to be a linear function. So this is going to be as plus b. Okay. And so from here, you're going to multiply by the denominator and solve for the all the coefficients. Okay. And so it is fairly time consuming, I know, because we have 4 terms here, and so we're going to end up with 4 different equations. But that's basically how you would set this one up, right? Did that help, Sean, with this problem? Okay, good. Yeah, I think the majority of the work is here in the partial fractions, but I think once you kind of set it up, it's kind of good from there. Okay. All right, let's go back to impulse functions. Just kind of make sure that we can. I want to make sure I finish the impulse function. It's not that much, and so we'll probably have more time at the end of class today to answer more questions about either the homework or the midterm. But I wanted to make sure I finish impulse functions today so that you can have that prepared for the homework and for the exam, of course. All right, impulse functions. All right, so what we saw last class was that, when we use Laplace, we can make use of these kind of special functions for the forcing term to kind of model some common engineering situations. Okay. Okay. And so far we've covered step functions, and the main utility of step functions was that it allowed us to model a phenomenon that could be turned on and off. Okay. And so we saw that on Tuesday. So when we did our circuit example, we did an example for when you can basically switch the battery on and off, and we saw what effect that had on the solution. Okay. Impulse functions kind of belong to the same category. So impulse functions are a special forcing function. But what they are really good at modeling is they're good at modeling that takes effect only for a very brief instant of time. And if you model the impulse function, you'll kind of understand what that means. Okay? You might have seen this function before in a previous class, maybe in a physics class, but this special function that we're going to be looking at is called the Dirac delta function. Okay, so Dirac delta is another form, or it's another name for the impulse function. Okay, and so usually the form for the Dirac delta function that we use is a delta, and then it's going to be t minus a. Okay, so visually it looks like this, and so we have our time domain here, t, and then when t is equal to a, it's a little bit hard to draw really well, and so inevitably, when you draw it on paper, it almost looks like a cone, right? Okay, and so basically the function is 0 everywhere else. And then when t is equal to a, it spikes up. Okay, so when I draw it, it looks like a cone just because that's just the way I draw it. But in reality, it's really just a spike that occurs at just an instantaneous time. Okay, so everywhere else this function is 0 except at the time a. That's when the function spikes up. Okay, and so if you were to kind of model this or kind of write it out as a function, we have delta of t minus a is equal to. Okay. There's two possible values, and so when t is not equal to a, okay, the function is equal to 0. And then technically speaking, when t is equal to a, the function value is infinity. Okay. So it's really almost like an infinite, almost like you can consider it an infinite amount of forcing for a very, very brief instant of time. Right? So of course, mathematically, this is nonsensical, right? So you can't have a function with an infinite value for just a brief instant of time. And, this is typically not how we use it. And so typically the Dirac delta function, you don't really use it by itself. You really use it, in combination with an integral. Okay. Okay. So there are two, I would say, kind of important integral properties for Dirac deltas. Okay. So first is just the integral of the Dirac delta itself. And so if we take the integral, we can even do from minus infinity to infinity, okay, of delta t minus a dt. Okay. So the Dirac delta is defined in such a way that even though the function value itself is infinity, it also takes place over such a brief instant of time that brief instant of time is basically 1 over infinity, right? And so the area under the Dirac delta curve is actually just 1. Right? So it's a function with an infinite value, but also an infinitesimally small duration. And so, that's why we end up with a integral of 1. Okay. The other property that is useful for is called the sifting property, and this is the one that we'll actually use with Laplace transforms. Actually, let me label this. Let me label it like this, and so we'll say this right here, area under delta curve. Okay. The other property that the Dirac delta has is that if you multiply the Dirac delta by another function and you integrate that, it's basically the same thing as evaluating that function wherever that delta pulse is. Okay. And so mathematically it looks like this. And so we have integral from minus infinity to infinity of some function, so we'll call it g of t. Okay. So this g of t can be any function. As long as it's a function of t, we can multiply it by the Dirac delta. Okay. And so if you integrate that g of t multiplied by the Dirac delta of t minus a dt, what this is equal to is that you basically take the a, or wherever that pulse is, at the location of the pulse, and you plug that into g of t. Okay. And so the result of this integral is g of a. Okay. So this is called the sifting property. Okay. Go away, you little shit. I'm teaching a class. Hi. My cat is nibbling my toes. You don't see my cat. That's my cat. His name's Potato. Okay, so that is that's the area property, and that's the sifting property of the Dirac delta functions. Okay. Any questions on this so far? Okay. All right. So those are the properties. And so let's talk about what Dirac deltas are useful for. All right, so impulse functions are primarily used for physical situations or physical forcings that take place over a very brief instant of time. Okay, so here's some examples, and so you can come up with many more, but here are just some examples that just to kind of get the conversation started. Okay. Okay, so the most classical example for an impulse function, and the one that's I think mostly used in physics classes, is if you have a mass spring damper system and you strike it with what they call a hammer blow. Okay, and so if we draw a mass spring, okay, so you have a mass that's attached to a string, right? A hammer blow is literally, you take a hammer or some kind of blunt object and you strike the mass, right? And so you basically take, a hammer and you strike it. Okay. The reason this is modeled with an impulse function is that if you look at the amount of contact time the hammer actually has with the mass, it's very small, right? And so you're swinging the hammer really fast, you hit the mass, but as soon as you make contact with the mass, it starts to move away. Okay, and so the amount of time that you actually apply the forcing is really small, right? But at the same time, you hit it, you strike it with such force that that strike, even though it's only in contact with the mass for a short amount of time, is still going to cause the mass to to react, right? And so you can imagine this too. So you take like a mass spring, you punch it or something like that, and then it's going to start oscillating, right? And so that's basically that's the quintessential situation of what can be modeled with an impulse function. Okay, and so another example, this one's a bit more practical. So let's say that you're driving, very quickly in the parking lot, and let's say that you very suddenly kind of hit a speed bump. Okay. Okay. And so when you go over a speed bump, that's going to cause the shock absorbers or the in your car to react. Okay. And so it's very similar. And so the amount of time that you actually strike the speed bump, is very brief, right? But then that brief instant of time is going to cause your system to react. Okay. Okay, and then number three, let's do an example from let's do a non-structural example. If we think about heat transfer, if you think about the amount of heating that can occur from something, right? If you have a combustion reaction, which is something that happens very common in your car, right? The combustion reaction only occurs over a very brief instant of time, right? So it's basically just kind of a localized explosion, okay? But that localized explosion is going to cause heating in your object, which we can model using an impulse function. Okay? And so we'll do an example later today showing that case. Okay, so look at the equations of heat transfer. We'll look at the forcing that's due to a combustion reaction, and we'll see how that affects the temperature in a combustion chamber over time. Okay, so these are just a few examples, but hopefully, and there are many more, infinitely many more, but hopefully this kind of gives you a sense of what impulse functions are designed to do. Okay, so basically any kind of forcing, any kind of external forcing that only impacts or only affects your model or your system for a very brief instant of time, that's basically what impulse functions are designed for. Okay, and so if you compare this to step functions, where step functions are forcing functions or forcings that can be turned on and off. Okay, impulse functions are things that only happen over a very brief instant of time, and so that's the main point of today. Okay. All right, any questions on this? Okay, all right, so let's see how this interacts with Laplace. Okay, and so of course, our ultimate goal is to, incorporate these impulsive forcings or these direct delta forcings into our governing differential equation. Okay, and so let's see how that works out. So before we can do that, of course we need to be able to take the Laplace transform of an impulse function. Okay, so let's start with that. Okay, and so if we take the Laplace transform of a direct delta, we end up with, let's write out the equation. So the equation is integral from 0 to infinity, e to the minus st multiplied by delta of t minus a dt. Okay. And so we need to evaluate this integral in order to take the Laplace transform of a delta function. Okay. All right. And so to do this, it's actually very simple. And so if you look back in your notes at the different properties of of the Dirac delta, you can see that we're going to make use of this property here called the sifting property. Okay, and so here our g of t is equal to e to the minus st. Okay, and so when we evaluate this integral, the only thing that we're going to do is we're going to replace t with a. Okay, and so the result of this integral, we don't even have to do any integration. That's kind of the nice thing about the Dirac deltas, is that we end up with e to the minus s. Okay, and then for t, we're going to plug in a, which is the location of the pulse. Okay, and so the Laplace transform of delta t minus a is just equal to e to the minus sa. Right, so very simple, right? And so it's even simpler than a step function. And what you'll see is that solving problems with the impulse function is a lot simpler as well, because there's a lot less partial fractions that you have to do with the impulse function, which is I think a good reason to celebrate. Okay. Okay, so let's do a very quick example then. And so let's do an example where we have a mass spring damper system that's subjected to a hammer blow. Okay. All right, so let's write out the differential equation. So the differential equation for this is y double prime plus 3y prime plus 2y is equal to delta t minus 1. And let's assume that we start completely from rest. And so both the initial function and the initial derivative are going to be 0. Okay, so we have y of 0 is equal to 0, and then y prime of 0 is equal to 0. Okay, so simplest case that we can imagine. All right, so just like we usually do with Laplace, let's go ahead and take the Laplace transform of this entire equation. Okay, so we take the Laplace transform of y double prime plus 3y prime plus 2y is equal to delta Laplace of the delta t minus 1 okay. All right, so let's go ahead and carry out this Laplace. And so first we have the Laplace transform of y double prime. And so that is s squared, big Y of s, minus s y of 0 minus y prime of 0. Okay. Then we have a Laplace transform of 3 y prime. And so the Laplace transform of that is s y of s minus y of 0 plus 2 Laplace transform of y is just y of s. Okay. And then we have the Laplace transform of delta t minus 1. So let's use our formula up here. Okay. So Laplace transform of delta t minus a is just e to the minus sa. And so in this case, our a is equal to 1 because the delta is only offset by by a time of 1. And so we end up with e to the minus s. Okay. Okay, so let's go ahead and plug in our initial conditions here. Okay, and so the good thing about this problem is that all the initial conditions are 0, and so all of those are just going to go away. Okay, and so on the left-hand side, all we're left with is y of s multiplied by s squared plus 3s plus 2. Okay, And this is equal to e to the minus s. All right, so now that we have applied Laplace transform to the equation and we've simplified it as best we can, let's go ahead and solve for y of s. Okay. And so for this case, it's pretty simple. And so all we have is that quadratic expression on the left-hand side. And so let's divide by that. And so we have y of s is equal to e to the minus s divided by s squared plus 3s plus 2. Okay. Let's go ahead and factor out that denominator. And so the denominator is going to be factored to s plus 1 times s plus 2. Okay. And now all we have to do is just invert this. Okay. All right, but we're in luck. And so, the fact that our impulse function here is only an exponential means that our inversion is going to be a little bit easier. Okay. Because we know, if you remember from Tuesday, that if you ever see an exponential term in the Laplace transform, all this is going to do is it's going to cause a shift in the time domain. Okay. And so this here is our t shifting term. Okay. But if you remember from Tuesday too, that when we have these exponential terms, we don't factor them directly into the inverse. And so what we like to do is we take the inverse of kind of the base function. Okay. Okay. And so if we neglect the e to the minus s here, our base function is just 1 over s plus 1, s plus 2. Okay. So let's take the inverse. We're going to take the inverse of that first, and then after we take that inverse, then we'll apply the t shift. Okay. Okay. And so, this part here is really important because I know when you're looking at these Laplace expressions and, this one's not so bad. We have just one exponential, but, when you go to do the homework and things like that, right? And if you look at the example we did at the end of class on Tuesday, there can be a lot of exponential expressions, depending on how many step and impulse functions that you have, right? And it can look intimidating, right? And so it could look like you have kind of an overwhelming kind of amount of math that you have to do. Okay. And so whenever you see, and so, that's kind of why I tell you this, and that's kind of why I told you my two-step process from Tuesday, right? Whenever you see an exponential function in the Laplace domain, just kind of ignore it at first, right? And so just kind of pretend it doesn't exist. Go ahead and take the inverse Laplace of the base function of just whatever's left. And then after that, then you apply the t shift. Okay. So I think if you do that, then I think it becomes a lot more palatable. It becomes a lot more easy to kind of see how it happens. Okay. Okay. And so with that said, let's follow the same process here. So let's ignore the e to the minus s for now, and let's take the inverse Laplace of this base function, 1 over s plus 1 times s plus 2. Okay. Okay. But as it is right now, we can't take its inverse Laplace. So let's go ahead and break it up into two terms. Okay, so let's take partial fractions. Okay. Right, so we're going to break it up into one term with s plus 1 and another term with s plus 2. Okay. Okay, so let's go ahead and multiply by the denominator here. And so if we do that, we end up with 1 is equal to a times s plus 2 plus b times s plus 1. Okay. let's go ahead and group the like terms. And so if we group the like terms from here, we have 1 is equal to S times A plus B plus the constant term 1 multiplied by 2A plus B. Okay. All right, so let's go ahead and set up our equations. And so we have an equation for S. We have an equation for the constant term. Okay. And so for S, we have A plus B is equal to 0. And then for the constant term, we have 2A plus B is equal to 1 from the left-hand side. Okay. Okay. And so we have our system of two equations here. And so we can solve those two equations for A and B. Okay. So I'm going to go ahead and skip to the result because this system is fairly easy, but you can imagine you solve the first system, you get A is equal to minus B, you plug that into the second equation and you can solve that one for B. Then once you have the solution for B, you just plug that back in for A. Okay. And so the result of this is we get A is equal to 1 and B is equal to minus 1. Okay. And so from our partial fraction decomposition, we get 1 over S plus 1 times S plus 2 is equal to 1 over S plus 1 minus 1 over S plus 2. All right, so let's go ahead and take the inverse of this. Okay. And so if we invert each term, let's invert the 1 over S plus 1 first. And so that's going to be e to the minus t. Okay. And then let's invert the 1 over S plus 2. And so that's very similarly an exponential function, except that's going to be e to the minus 2t. Okay. Right. And so this e to the minus t, this was the 1 over S plus 1. And this e to the minus 2t, that's 1 over S plus 2. Okay. Okay. All right, so now let's combine this together with the t shifting, because if you remember, our y of s up here had that e to the minus s up top. So let's move that down here. So y of s is equal to e to the minus s divided by s plus 1, s plus 2. Okay, we've already inverted the base function, and so the base function, we're going to have e to the minus s multiplied by e to the minus t minus e to the minus 2t. Okay, so this right here is our inverted base function. Okay, so that's what we just finished doing with the with the partial fractions. Okay. Now let's apply the t shifting to each of the terms. And so we're going to apply a t shift of t minus 1 to each of these two expressions. Okay. And so the e to the minus s will cause a t shift of t minus 1 to each term. Okay. So let's go ahead and do that. And so remember, when we apply a t shift, we basically replace t by t minus 1. Okay. And so our final expression for y of t is going to be equal to, first we have e to the minus t. And so instead of e to the minus t, we're going to have e to the t minus t minus 1. Okay. And remember, the other thing we have to do with t shifting is we have to multiply it by the corresponding step function. Okay. Okay, so I have e to the minus t minus 1 times u of t minus 1 minus e to the minus 2t. But again, we're going to replace the t there with t minus 1. And so e to the minus 2 t minus 1. Okay. And then we're going to multiply it by the step function. So u of t minus 1. Okay. So remember, the reason we multiply by the step function here is the fact that this impulse doesn't occur until t is equal to 1, right? Okay. And so that means that, and in this particular problem, both of our initial conditions are 0. That's not necessarily the case, for every function, but for this one in particular, both our initial conditions were 0. Okay. And so that means the only source of forcing, so the only thing that's going to cause the system to react is not going to occur until t is equal to 1. So until t is equal to 1, we can say that our mass spring damper system is just chilling. Okay. Okay. And so, because of this, our solution needs to reflect this fact, right? And so our solution shouldn't have any kind of behavior. It shouldn't have any kind of action, you should say, before t is equal to 1, right? Okay. And so that's the reason why we have these step functions as part of the result, right? And remember, what the step functions are going to allow us to do is that it's going to basically eliminate everything before t is equal to 1. Okay. So that's why we have these. Okay. And so whenever you apply t shifting, don't forget the step functions as part of the result too. Okay. So whenever you apply your t shift, not only do you replace the t with t minus a, but then you also have to multiply by the step function u of t minus a as well. Okay. So don't forget that. And so remember, the main reason why we do that is because of this reason that I've kind of laid out here. Okay. All right. Any questions on this example here? Okay. All right, so that's kind of our first example with impulse functions. Okay, so you can see that with the exception of the t shifting, at the end of the day, it's not that bad, right? And so hopefully you'll see that this is a bit easier than step functions. Okay. All right, so let's talk about another property of the impulse function, but now let's connect it back to our step functions. Okay. So let's draw both functions here, and let's see if we can form a connection between the two, because actually the two functions are very closely connected. Okay. So let's start. Well, I should have said step versus impulse function. Well, actually, let's do this. Let's do impulse function on the left. Okay. So our impulse function is going to be delta t minus a, and then our step function will be u of t minus a. So let's start by graphing them, and let's see if we can find a relationship between their graphs. Okay. So for the impulse function, we know what that looks like because we've already drawn it today. Basically, the impulse function is going to be 0 everywhere. Okay. Up until you reach t is equal to a, and then it's going to spike up. And it's going to be 0 everywhere else. Okay. And remember, the height of this peak or the height of the spike is basically infinity. Okay, so it's infinity for a very brief instant of time, and then comes back down to 0 after that. Okay. The step function, on the other hand, up until t is equal to a is going to be 0. Okay. So both the impulse and the step function kind of share that property in common. Okay. So there's 0 up until a certain point, and then once you reach that certain point, it goes up, right? But then the step function, in contrast, is going to persist after t is equal to a, and so it's going to look like that. Literally going to look like a step. Okay. Right, so those are our two special functions. Okay. Let's look at the step function first. Okay. In particular, let's look at what the slope of the step function is at t is equal to a. Okay. All right. So let's look at our step function. So step function is basically 0 up until t is equal to a, and then once t is equal to a, we basically shoot up to a value of 1, right? And so geometrically, if you look at this function here, at t is equal to a, okay, we basically have a vertical line. Okay. All right, and so if you remember from calculus, when you have a vertical line, what's the slope of a vertical line? So what's the rise over run for a vertical line? It's infinity, right? Undefined, exactly. Right? Okay. And so that's interesting, right? Because and for that reason, these step and impulse functions, some people call them engineering functions because they're not, they have kind of very weird properties that don't really follow the rules of a lot of math. Okay. And this is kind of one reason, right? And so for most functions, you're not going to have a vertical line like this. Okay. All right. And so let's relate that to the impulse function, right? And so what's the value of the impulse function at t is equal to a? Okay. We've already talked about earlier that it's basically infinite, but infinite doesn't really, mathematically it does not exist, right? And so, it's kind of a mathematical, approximation, I guess you could say. And so another way that we can say it is that, the value of the impulse function at t is equal to a is also undefined. Okay. So hopefully you're starting to see kind of the relationship between the step and impulse function, right? So basically the relationship is this. And so, we know that the slope of the step function is undefined at t is equal to a, and we know the value of the impulse function is also undefined at t is equal to a, right? What's another way that we can mathematically represent the slope? It's with a derivative, right? And so if we take the derivative of the step function, okay, this is going to get us the impulse function. So that's the relationship between these two functions. And so, the impulse function is basically just the derivative of the step function. Okay. Or at least as close as we can get to it, right? But the interesting thing is that we can actually prove this relationship with Laplace as well. Okay. It's a very short proof, don't worry, it's not going to take that much time. But if you remember, and we've been using this in our in our differential equations as well, that if you take the Laplace transform of a derivative, okay, taking the Laplace transform of a derivative gets us s times f of s minus little f of 0. Okay. So let's apply that to our equation up here. Okay. So this is kind of like an alternative form for finding the Laplace transform of an impulse. Okay. So we've already kind of shown it above. We did that like 20 minutes ago, but this is kind of an alternative way. Okay. And so let's take the Laplace transform of d dt of u of t minus a. Okay. And so first, let's take the Laplace transform of u of t minus a. Okay. So the Laplace transform for this we know is e to the minus sa divided by s. Okay. So let's plug that in up here. And so this is going to give us s times the Laplace transform of u of t minus a. So that e to the minus sa divided by s, okay, minus u of t minus a evaluated at 0. So u of 0 minus a. Okay. So let's go ahead and simplify this expression. And so we know u of 0 minus a, this is 0, right? Because the step function, it has a value of 0 up until we reach that value of a. Okay. And if we assume a is a positive number, then that's going to be 0. Okay. From here, these s's are going to cancel out. And so the Laplace transform of d dt of u of t minus a is equal to e to the minus sa. Okay. And coincidentally, a little coinky dink, if we look at the Laplace transform of delta, okay, we've already shown above that that's also equal to e to the s minus sa. Okay. Okay. So this is a very short proof. It's kind of a cute proof. It's very simple to kind of show that we have this mathematical relationship between step and impulse functions. Okay. So impulse functions is just the derivative of the step function. Okay. All right. Any questions on this little proof here? Okay. All right, I have one more example for you guys. And so this is kind of a more physical example. And so let's talk about that heat transfer situation where we talk about the sudden heating that occurs from a combustion reaction. Okay. All right. So let's draw this visually. So we have our combustion chamber. I know this is not what a real combustion chamber looks like, but this is the limits of my artistic ability. Okay. So we have a combustion chamber that is a box. Okay. And a combustion reaction, like we said before, is basically just a localized explosion, right? So we have basically, we combine together all the constituents. You have fuel, you have oxygen, and you give it a spark. And so that's going to cause a little combustion reaction. Okay, so we have basically a little explosion here. We'll go fancy. We'll go 3 colors. Okay. Our little fuzzball of an explosion. Right? And so if we assume that this combustion chamber, it starts at rest, right? And so basically we assume that the combustion chamber starts at room temperature, then after this combustion reaction occurs, then it's going to cause some heating, right? So it's going to heat up this combustion, this chamber. Okay. Okay. And so what we want to do is we want to model this, okay? And so we basically want to solve the equations for heat transfer, regarding this this explosion, and we want to get an equation for what the temperature of the chamber is going to be as a function of time. Okay. All right. One other thing that we'll need to have for this equation is, or for the system, is we need to have some place for the heat to go, and so we're gonna use convection cooling on the outside. Okay, so we're going to assume that we basically have air, cool air on the outside that's cooling this chamber. Okay. Okay. And so I know most of you probably haven't taken heat transfer yet, but basically the way that this works is that whenever you have some kind of fluid or some kind of air or water that's kind of cooling from the outside, the way that we mathematically model this is through a convection coefficient, right? And so we need 2 variables here. So we need H and T infinity. Okay. All right. Okay. So that's basically our situation. So, again, I know not everyone's taken heat transfer, but, physically, I think what's more important is just to kind of get the physical intuition of what's going on, right? So we have a combustion chamber, and so you can consider it just like a aluminum box, I guess you could say. Inside that box, we're causing a kind of little miniature explosion caused by the combustion reaction, right? And so that combustion reaction is going to cause the chamber to heat up, okay? But at the same time, outside the box, we have cool air that's kind of cooling the box at the same time. Okay. And so you have kind of 2 opposing forces. And so on the one hand, we have the explosion that's going to heat up the chamber, and then we have the cool air on the outside that's going to cool it down. Okay. And so what we should see is that if you look at the results, we should get a sudden spike of temperature when the combustion reaction takes place. Okay. But since that combustion reaction only takes place for a very brief instant of time, eventually the temperature is going to come back down because of the cooling that occurs from the outside. Okay. So that's kind of what we expect. And so, the mathematics of when we solve this should reflect that fact. Okay. So let's go ahead and solve this equation. Okay. Okay. And so our equation for the chamber temperature is given by the following. So we have dt, okay, where big T here is temperature, little t is time, plus H times big T is equal to delta T minus 3. Okay. Okay. And so this delta T minus 3 here, this is basically telling us our combustion reaction is taking place at T is equal to 3. Okay. And so let's give it an initial condition. And so let's say that T of 0 is equal to T naught. Okay. And so this equation here, I'm going to be doing mostly in terms of symbols, but that is the that's kind of how these are. Okay. Okay. So we have our differential equation here, and so now we can solve it, right? And so since we have an impulse function on the right-hand side, that means we have to solve this using Laplace. Okay. All right. So step 1. Let's take the Laplace transform of this entire equation. Okay. So we're going to take the Laplace transform of the left-hand side, and then that's equal to the Laplace transform of the right-hand side. Okay. So let's take the Laplace transform of the left, and so we have the Laplace transform of dt. Okay. And so that's going to be s big T of s minus T of 0. Okay. This is a little bit of a change of pace because this is only a first order equation. And so everything up to this point, we've done second order ordinary differential equations, but this was only first order. Okay. This one's actually quite similar to the homework problem. And so the homework problem, I believe I also gave you a first order equation. Okay. And then we take the Laplace transfer of ht, and so that gives us h times t of s. And this is equal to the Laplace transform of delta t minus 3. So that's e to the minus 3s. Right. So once again, we end up with an exponential term. And so that's going to cause a t shift kind of once we're all done with everything else. Okay. Okay. All right, so we have this T of 0 here. So let's go ahead and plug in our initial condition. And so our initial condition here is T naught. Okay. And so let's group the values of T of S on the left-hand side. And so we have T of S multiplied by S plus H minus T of 0 is equal to e to the minus 3s. Okay. So now that we've done that, let's go ahead and solve this equation for T of S. So let's move that t0, t0 over to the other side of the equation. So we have t of s times s plus h is equal to e to the minus 3s plus t0. Okay. Let's divide both sides by s plus h. And so we get t of s is equal to e to the minus 3s divided by s plus h plus t0 divided by s plus h. Okay. All right. So the good news here is that, because we are a first order equation, and we only have impulsive forcing, there's no partial fractions that we have to do. Okay, so we can just kind of straight up invert this because we have 1 over s plus h on both of our terms here. Okay. Okay. So let's go ahead and do that. And so we have the Laplace inverse of 1 over s plus h. Okay. I'm doing this once separately just because both of our terms up there have are basically the same. Okay. Remember, the first term has e to the minus s, but that's the result of that is just going to be a t shift. Okay. The base function is still the same. So the Laplace inverse of this is e to the minus ht. Okay. So let's go ahead and apply that. So we have t of t is equal to, I'm not going to do the t shift yet, so we'll do that in a second. So we have e to the minus s multiplied by e to the minus ht plus t0 e to the minus ht excuse me, this should be e to the minus 3s. Sorry about that. Yes, thank you. Thanks for catching that. Okay. All right, and so the last thing we need to do here is we need to apply our t shifting. Okay. And so we're going to replace every instance of t with t minus 3, and we're going to multiply by u of t minus 3. Okay, so we have t of t is equal to e to the minus h times t minus 3 u of t minus 3 plus t0 e to the minus ht. All right, and so that's our result. Okay. Any questions on how we did this example here? Okay. All right, so this is a good example to kind of end with because I want to kind of show you a little bit about the result here, right? And so if you remember from our last example, we talked about the effect of the step function here. Okay, and so I modified this example a little bit from what's in the notes because I want to kind of highlight something that's important here. Okay, because if you look at our two terms here, and so you have one term here, of course, and another term here. Okay. Let's think about where these terms came from in terms of kind of the initial parameters of the problem. Okay. And so this first term, this e to the minus h t minus 3 u of t minus 3, okay, this part of the solution came directly as a result of the impulse function. So this came directly from the combustion reaction, where if you remember from the beginning of the problem, the combustion reaction occurred at t is equal to 3. Okay. And so if you look at the kind of the characteristics of this term in the solution, that makes a lot of sense, right? And so remember we talked about before that, nothing, the result or the reaction from a forcing, either an impulsive forcing or a step forcing, can't occur until that forcing actually occurs, right? And so since this forcing doesn't occur until t is equal to 3, it makes sense that this part of the solution has this u of t minus 3, okay? And so this does not take effect until t is equal to 3 due to u of t minus 3. Okay. Right. So intuitively, that should make sense, right? And so, whenever you have any kind of impulsive forcing or any kind of step forcing that's occurring at some time in the future, right, then the solution can't really react to that until that forcing actually occurs. Okay. And so, kind of use that as kind of like a mental check for whenever you're doing these kinds of problems with step and impulse functions. Okay. On the other hand, we have the second term here. Okay. And if you kind of trace back the math kind of from where we came from, this term here came as a direct result from the initial condition. Okay. And so if you compare it to our first term here, there's no step function. There's no u of t minus something, right? Because if you think about it, the initial condition is there from the very beginning of the problem. Okay. Okay. And so since the initial condition was present from the start, then the solution can react to it, starting from t is equal to 0, right? And so that's why we don't have any step function here. Okay. So it's kind of a subtle point, but it's one that I hope you guys take away from this week, where what's unique about these step and impulse functions is that they can provide forcings that happen sometime in the future. Okay, that's kind of the main utility of step and impulse functions, is that before this, when we were doing just differential equations by itself, we either had our initial conditions or we had forcing functions that was persistent throughout the entire time. Okay. Now with step and impulse functions, we can provide forcings that occur at discrete times that we can either occur just very quickly, or something that we can turn on or off. Okay. And that utility is actually very key, because there's a lot of engineering situations that kind of fall into that category. Okay. All right. Any final questions on this before we wrap it up for the week? Okay, all right, so that's all I got time for today. So thank you guys again for meeting virtually today. The recording will be up very soon. So thank you guys for that. So hope you guys have a good weekend. Remember, homework 3 is due on Sunday. I also kind of pushed it back a little bit because I am going out of town for the next 2 days, so Friday, Saturday. And so if you have questions on the homework, I do have office hours after this, so definitely feel free to stop by. But if you have questions over the weekend, I'll try to get back to you, as soon as I can on Sunday. So I'm driving back on Sunday, and basically when I get back, I'm probably going to be expecting a mountain of emails, and so I'll do my best to get back to you on there. Okay. So hope you guys have a good weekend. Best of luck, studying, and I will see you guys next week.
Professor,
Yep. What's up?
what day is our midterm? I'm sorry, I forgot.
It's Thursday, so it'll be next Thursday.
Okay, excellent. Thank you.
Yep.